Okay, so we have to ask a question. How big is a unit? Okay, what is a meter? What is a second? And how do we know we're defining it precisely? For the vast majority of human history, measurements were not very precise. So, for example, according to folklore, a foot was the length of a king's foot, okay? And as you know, if you just walk into a shoe store, the length of various feet are preposterously different, right? So you could have a building collapse or a bridge collapse because, from one king to another, the foot that they're talking about in the plans to make such a building or a bridge changed completely, okay? So we need to make this very precise. And to kind of drive home how precise it needs to be, one example is that there is a lab in Massachusetts that is probably the coldest place in the entire universe. Unless there's aliens somewhere making something even colder, there are people in Massachusetts who have gotten a sample to go down to a temperature of 10 to the minus 9 or a billionth of a degree Kelvin. And you guys know that is just, a billionth of a degree above absolute zero. So differences in temperature at that point are extremely important and very, very precise, right? So how do we get precise? So if you guys will advance to the slide that says a meter is derived from the speed of light, okay? So it turns out that we have derived the length of 1 meter from the distance that light will travel in 1 over 299,792,458 of a second. So what is significant of this number, 299,792,458? That's just the speed of light, okay? So in the future, I'm just going to expect you guys to know that the speed of light is 3 times 10 to the 8. We're kind of rounding this just to a 3 meters per second. But this is the precise version, and if we want to get to a meter in very precise terms, we want to use this, right? So here's the deal, right? You guys maybe know that speed is equal to distance divided by time, right? Which means that time is equal to distance divided by speed. So if I'm looking at 1 meter, if I wanted to find 1 meter, then I would take 1 meter and divide it by the speed of light, 3 times 10 to the 8, or basically this, just put this in there, right? So this would be the time interval. 1 meter would be the distance that light travels in this little time interval right here, okay? And as you can see, that's going to get a meter to a very, very precise measurement, okay? All right, why do you think that we use the speed of light to determine length? I'll give you a second to think about it. The bottom line is, it doesn't change. It never changes. It's always the same, and it's something we know very precisely. It's not like the king's foot. Okay. All right, moving on. What is a second? How do we know what a second is? Okay. Well, turns out that we define the second from the frequency of light emitted from a certain cesium atom. So you guys probably know that if I have a nucleus over here, right? And it has these different orbitals, these different energy levels, right? And that if I excite an electron in that energy level, it'll rise to a certain, energy state, right? And then it's metastable, so it'll fall back down. And in the process, it'll release a photon with a certain wavelength and a certain frequency, okay? Now, it turns out that 1 second is the time taken to complete 9,192,631,770 oscillations of a certain frequency of light emitted by a cesium-133 atom. Again, why do we use this to measure a second? Because it's incredibly precise and we know it and it never changes. Okay, so that's how we get a second. Pretty cool, huh? A much more clunky version is the kilogram, right? The kilogram, we actually created a sample that we decided is the precise kilogram. It lived inside of a vacuum, inside of a lab, inside of Paris for a very long time. It was basically just a little guy like this that was exactly 1 kilogram, and they kept it not in contact with air at all. But then they started checking it over the years, and for some reason, which they still don't fully understand, the mass was changing ever so slightly. And so we came up with a new definition of a kilogram based on Planck's constant. I'm not going to go into it right now, but I'm going to put a really cool video that explains and explores that switch to the Planck's constant unit with this wonderful YouTube channel called Veritasium. If you haven't checked it out, I totally would. They're great. Okay. Next, we need to figure out, now that we know what units are and we understand how to measure them and how to choose them, right? We want to always do our units in SI, right? The System International. And now we know precisely how we pick our main units. The question is, how do we convert from one set of units to another? And to do this, we have a very clever method called the ladder method. And that's what we're going to be tackling in the next video.